Studies on computer, share trick substitution. Hello, everybody. Hello, everybody. This is the Professor Ma, and this is the videos on trick substitution, section 19, I believe. Okay. In this section, we're going to wrap up all the tricky uh, different integrations that we've been doing. In particular, we've been doing some unit tests on integrating products of sines and cosines, integrating rational formula, which goes in the route of decompositions and integrate, okay? And then this trig substitution kind of wraps things up for us. That is what it's going to apply to use and apply to those cases. Okay. In particular, we're going to do integrates. We're going to integrate that expressions that contains this type of square root. What type of square root? Square root of second degree inside square root. Okay, if it's a second degree inside square root, then I can always change into this format by doing some substitutions, you know. So any well, have some later. Okay. And the first thing we notice that all these expressions related to the trig formula. Okay, so that means therefore we're going to do trig substitution, meaning that we're going to set x to be a trig function. I know it's kind of uncomfortable. So x likes x, what do I make it into a trig function? Well, that's what a trig is. Okay, so these are the trig substitutions. Okay, so if I have these expressions, if I were just cleverly to say set x to be this trigonometry function a times sine, then the things can be square root out of the square root. Okay. Okay, and so let's not worry about the domain and the range, etc. Okay, and then for these three patterns, we have these three different algebraic algebra. Okay, substitution that gives me a convert this expression into a trigonometric functions. Okay, so that's the first part. And secondly, related to each one of these substitutions I choose, and there is a picture goes along with it. Okay, a little chart or the reference triangle that tells me the relationship between an angle, triangles, and the substitutions. Okay, and in particular, if x is equal to, if I were to do this substitution, then I have sine theta that's x divided by a. And then this is a reference triangle for the angle theta. Okay, so if you want, if you want to say what's the theta relationship to the x, well, here's the picture for theta. Okay, in particular, then immediately I know what the first sites I can fill in, and then therefore from this picture I can recover every trig values of theta, cosine, tangent, etc. I read off the reference triangle. We did it. We have done this before. Okay. Theta x sine inverse xa. Okay. So this is the algebraic. Okay. That is a picture of low algebra. This is after substitution. I need this chart to lead me back into the answer to x. Okay. You will see. And so we have this picture for each one of the substitutions, so you can make, you know. It's easy to understand. Okay, let's do an example. The expressions that say, oh, this trig substitution can give us the answer is that you have the square root of a quadratic terms. And then the rest of the questions could be all kind of polynomials in x. Yeah, I think it should be, built. Yeah. Polynomials. That's good. Okay. So we're going to make a substitution in this case, x to be 2 sine over theta. Then the square will become cosine theta. Okay. And the 4 pulls out. And then we're going to substitute the x. of course, by sine theta. So they become trigs. And dx we're going to replace by d theta, and that's another trig functions. Okay, so dx d theta is 2 cosine theta. Okay, so dx is going to be replaced by these. Dx replaced by that, and the x replaced by theta. So in these ones, everything now become trigonometry functions. Okay, in sine or cosine, meaning that they're going to turn into an integral of powers of sines and cosine. Okay, and that's why we did the link up with the powers of sines cosine. So you do a little algebra and wind up integrating 4 sine squares, and then this will know how to integrate, and then it comes out. Okay, so comes out answer in theta. The original problem is in x. I'll need now to work my way back into the answer in x's. That's where the triangle comes in. We have the reference triangles. Therefore, I can read out what sine theta is, cosine theta is, all these individual trig values in terms of the x. Okay, and the theta itself is in the trig inverse function. So then I can put everything. Okay. So I have put that back and put the sine, cosine, theta back, and these are the answers. Okay. Here's another one. Okay, notice, okay, that the basic idea is to get the derivative like that, or somebody's take the derivative like it wind up to be like that. I mean, we need some sort of combinations of square root and x's and so on. So the derivative will put that terms in the denominator. But to make everything else that works out, remember we have to use the derivative of sine inverse. Okay, good derivative of sine inverse also is that type of formula. So it's some combination of these, I will get their derivative to be x squared minus x squared. Okay, so it's kind of interesting how we navigate back into these answers. Okay, here's another one. It seems like, oh yeah, I mean, it seems like that there should be some nice functions that can take the derivative gives me that, and that nice function should have x squared minus 9 on top. So when I take a derivative, it turns it in the bottoms. But how do I piece them together? Actually, we'll go to this trig substitution. Okay. First, notice I'm going to make the shorthand E is for secant tangent, because this one is going to involve secant and tangent. And so this time we set x to be secant, and then it comes out to be tangent. So the square root comes out. And the derivative of secant is secant 10, so I can solve for dx. It turns into secant 10. So these portions goes into that, okay? And then each one x squared goes into that. And of course, then I have this square root becomes the tangent. Okay, so dump everything in, and so the algebra clean up into sines and cosine. Okay, and so we're integrating cosine, so that one's easy. Okay, so we got the answer in theta. Now put it back in x. That's where the triangles comes in, the second part. Okay, it's yeah, the 2-part, you know. And interesting is how we do this. Okay, with parts of what we do this algebra, another part is these little pictures that help us to do the problem. Okay, and so that's the answers. Okay. And here's another one, use tangent. Okay, and just because it has the tangent is to do with some with something like derivative, something to do with that a squared plus b squared, something like that. Okay, and that any irreducible polynomial can be transformed into that Okay. So if I have that format, that is the denominator, then I can pull these trips. Oh, I change the tangents as tangent squared. Okay. And so got tangent squared plus 4, then it becomes secant. So, okay. So now the bottom becomes 4 secant squared again, right? 16e to the 4th. And then the top is the substitution itself, x, and yeah, it's the same thing as before. So now this becomes integrating cosine squared and put the x back. Okay. So on these are the basic, now you know the trick of doing these, okay? And then one thing that it helps us to do to finish up the whole slew of things we've been doing in these sections is that in the partial fraction decompositions, numbers, we have a polynomial px over qx. You're going to break it up into like a number over x minus a plus number over max minus b, and maybe a squared, stuff like that. And it could be a like this. Then it comes to irreducible parts. Ax plus b, oops, ax plus b over second degree, something x squared, irreducible something x, some numbers, and this is irreducible. Okay. So if I know how to integrate these, then I know how to integrate every fractional polynomials, because the front part already did with how to integrate all these. Check. Now we integrate the square parts with the irreducible square at the bottom. Okay. Oh, well, I'm breaking the two parts. Okay. Let me see. I don't know if I did it with the. Okay. And the part that will give us problem is if there's no x, then the problem is it's just straightforward tangent inverse. But if it's x, that's one that we're going to deal with. Okay, so let's see how we put it into tangent inverse. So we'll do complete square. Okay. Okay, let's first do a substitution. Okay, and so now it becomes u squared plus 1 underneath. Okay, there might be other shorter ways. Okay, now it breaks into nice denominator match tangent square in u squared plus 1. Match derivative of tangent inverse. Yeah. Okay. And the front part I can do a substitutions. Okay, and basically it just log. Okay, comes out log. So you go derivative. Yeah, and this is, yeah, it's pretty straightforward. Okay, and that wraps up for the stuff we're going to do integrations. Okay, bye-bye. Stop. And